The evolution of a revolution. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're tackling a very common and important question in cryptography. Did elliptic curve cryptography eliminate the Diffie-Hellman key exchange? In this comprehensive presentation, we will walk through the exact mathematics of both the classic and modern versions of this protocol, using small, simple numbers to make every step clear. We'll see that ECC was not a replacement, but a massive upgrade that took a revolutionary idea and made it practical for the modern world. The core question. So, let's address the question head-on. Does ECC eliminate Diffie-Hellman? The answer is a clear no. A better way to think about it is with an analogy. Diffie-Hellman is the recipe, and the underlying math is the main ingredient. Elliptic curve cryptography provides a new, vastly superior ingredient for the same classic recipe. It didn't replace the recipe for a secure handshake, it just perfected it. This new version is what we call ECDH, or elliptic curve Diffie-Hellman. The Diffie-Hellman recipe. The Diffie-Hellman protocol itself is a brilliant, 5-step recipe that is independent of the math used. First, Alice and Bob agree on some public parameters. Second, they each generate their own private secret number. Third, they use the public parameters and their private secret to create a public value. Fourth, they exchange these public values. Finally, they each use their own private secret and the public value they received from the other person to compute a final, shared secret. This 5-step process is the recipe we will follow for both our classic and modern examples. Part 1. Classic Diffie-Hellman by the numbers. Let's begin by walking through the original Diffie-Hellman protocol. The mathematical ingredient it uses is modular exponentiation. The security is based on the discrete logarithm problem. It is easy to calculate g to the x modulo p, but hard to find x from the result. For our example, we need to first agree on our public parameters. We will use a small prime modulus p equals 23 and a generator g equals 5. These two numbers are public knowledge and are not secret. Classic DH example. Step 1. Secrets. Following our recipe, the first step is for Alice and Bob to invent their own secret numbers. These must be kept private and never transmitted. Alice chooses her private key, A equals 6. Bob chooses his private key, B equals 15. Their goal is to use these numbers to establish a shared secret without ever revealing the numbers 6 or 15. Classic DH example. Step 2. Public keys. Next, they each use their private key and the public parameters to generate a public key. Alice computes her public key A by calculating g to the power of a modulo p in her case. That's 5 to the power of 6 modulo 23. 5 to the power of 6. When we divide the result by 23, the remainder is 8. So, Alice's public key is A equals 8. Bob does the same with his private key. B equals g to the power of b modulo p, which is 5 to the power of 15 modulo 23. This is a much larger number, but the result of the modulo operation is 19. So, Bob's public key is b equals 19. Classic DH example. Step 3. The exchange. Alice and Bob now exchange their public keys over the insecure channel. Alice sends the number 8 to Bob. Bob sends the number 19 to Alice. An eavesdropper, Eve, can see the public parameters, 23 and 5, and she can see the public keys being exchanged, 8 and 19. However, she is stuck. To break the encryption, she would need to solve the discrete logarithm problem. For example, by figuring out that the number 6 is the exponent that turns 5 into 8 mod 23. With large numbers, this is impossible. Classic DH example. The shared secret. This is the final step where the magic happens. Alice takes Bob's public key, B equals 19, and raises it to the power of her own private key, A equals 6. Her calculation is 19 to the power of 6 modulo 23. This is a huge number, but when we take the remainder after dividing by 23, the result is 2. Meanwhile, Bob takes Alice's public key, A equals 8, and raises it to the power of his private key, B equals 15. His calculation is 8 to the power of 15 modulo 23. This is an even more gigantic number, but the final result of the modulo operation is also 2. They have both independently calculated the same shared secret. The number 2 is now their shared key. The problem with the classic ingredient. The classic recipe worked, but it had a major drawback. To keep the discrete logarithm problem hard enough to be secure against modern computers, the prime number p had to be enormous, specifically 2048 or even 3072 bits long. Performing calculations with such huge numbers is slow and requires a lot of computational power. This makes it inefficient, especially for low-powered devices like smartphones. The ingredient was becoming too heavy and cumbersome for the modern kitchen. Part 2. Modern ECDH by the numbers. Now, let's see how the exact same recipe works with a modern ingredient, elliptic curve cryptography. The security is based on the elliptic curve discrete logarithm problem. It's easy to compute d star g, but hard to find d from the result. For this example, we'll use our familiar, toy, curve. Y squared equals x cubed plus 2x plus 2 mod 17, with our public generator point g equals 5, 1. These parameters are public knowledge, just like p and g were in the last example. Our ECDH lookup table. To make our example math easier to follow, we will again use our pre-calculated lookup table for our generator point g. This table shows the result of multiplying g by different numbers. For example, 4 times g is the point 3, 1, and 7 times g is the point 0, 6. In the real world, these calculations are done on the fly, but this table will allow us to focus on the protocol's logic. ECDH example. Step 1 Secrets. Following the same recipe, Alice and Bob must first invent their own private secrets. To keep things comparable, we will use small numbers again. Alice chooses her private key, A equals 4. Bob chooses his private key, B equals 7. As before, these numbers are kept completely secret and are never transmitted. ECDH example. Public keys. Next, they generate their public keys by multiplying their private key with the public generator point g. Alice computes her public key A equals A times g, which is 4 times g. Looking at our table, we see the result is the point A equals parenthesis 3, 1 parenthesis. Bob computes his public key B equals B times g, which is 7 times g. Our table shows the result is the point B equals parenthesis 0, 6 parenthesis. These points on the curve are their public keys. ECDH example. Step 3 The exchange. Alice and Bob now exchange these public keys over the insecure channel. Alice sends the point 3, 1 to Bob, and Bob sends the point 0, 6 to Alice. An eavesdropper can see the public curve parameters, the generator G, and both public keys A and B. However, she is trapped by the ECDLP. She cannot figure out that Alice's secret number is 4 or that Bob's is 7. She cannot reverse the point multiplication. ECDH example. Step 4 The shared secret. Now for the final calculation. Alice takes Bob's public key, B equals 0, 6, and multiplies it by her private key, A equals 4. Her calculation is S equals 4 times B. Since we know B is just 7 times G, her calculation is really S equals 4 times 7 times G, which is 28 times G. Since our group order is 19, this is equivalent to 9 times G. Our lookup table shows that 9 times G is the point 7, 6. Meanwhile, Bob takes Alice's public key, A equals 3, 1, and multiplies it by his private key, B equals 7. His calculation is S equals 7 times A, which is 7 times 4 times G, which is also 28 times G. or 9 times g, he also gets the point 7,6. They have successfully computed the same shared secret point. The x-coordinate, 7, becomes their shared secret. Side-by-side comparison. This slide makes the distinction perfectly clear. The protocol, the recipe, is named Diffie-Hellman. The specific implementation depends on the mathematical ingredient used. The classic version uses modular exponentiation, while the modern version uses elliptic curve point multiplication. Because the ECDLP is a harder problem, it allows us to achieve the same security with much smaller keys, leading to a massive performance increase. When people say Diffie-Hellman in a modern context, they almost always mean ECDH. The efficiency payoff. Just how much more efficient is the new ingredient? The difference is staggering. A 256-bit ECC key provides the same level of security as a 3072-bit key in the classic Diffie-Hellman or RSA systems. This isn't just a small improvement, it's a game changer. Smaller keys mean the calculations are orders of magnitude faster, consume less power, and require less data to be sent over the network during a handshake. This is what made secure communication practical for the billions of mobile and IoT devices that make up the modern Internet. Conclusion. The perfected recipe. So, to return to our analogy, ECC did not throw out the revolutionary Diffie-Hellman recipe for key exchange. Instead, it provided a far superior ingredient that is stronger, lighter, and more efficient. By swapping out the old, heavy math of modular exponentiation for the new, powerful math of elliptic curves, we created elliptic curve Diffie-Hellman, ECDH. This perfected recipe is now the undisputed standard for key exchange in virtually all modern security protocols, from TLS 1.3 to your favorite messaging app. Final thoughts. Understanding the distinction between a protocol and the mathematical primitive it uses is key to understanding modern cryptography. The Diffie-Hellman protocol was a paradigm shift in thinking, and the development of elliptic curve cryptography provided the perfect tool to realize its full potential for a fast, interconnected world. The story of DH to ECDH is a perfect example of how great ideas in science and technology build upon and enhance one another.